Okay, students, this is our last class. So let's see the remaining part. So let me have a quick relook into what we discussed in the last class. It was about how to calculate entropy change of an ideal gas for various conditions, and we have defined these two equations. Solve one simple problem. One problem is given to you as a homework. Just go through that. A reversible polytropic process for an ideal gas. So we have developed some combination of properties, and we solved one problem on polytropic compression of an ideal gas. So up till this we covered in the last class. So let's draw it on the PV diagram. So as you know, so this is a compression process. This wasn't covered in the last class. So state point 1 to state point 2 as mentioned in the diagram there, 1 to 2. The corresponding pressure was given. The same thing can be drawn on TS diagram. So P1 and T1 are given 100 kilopascal and 20 degrees Celsius. So here it is 100 kilopascal and this is 20 degrees Celsius. And compression leads to a pressure increase of 500 kilopascal. So here it is 500 kilopascal, and we need to find the value of T2, and by calculation this is obtained to be around 425 Kelvin. So once we obtain this temperature after compression, these are the diagrams that are given here. So the area below the graph indicates the amount of work done from 1 to 2, and area below the graph represents the amount of heat transfer. Okay, so which was shown over here. Okay, so this is what we have covered in the last class. Again, we defined what exactly we mean by entropy generation, so that it can lead to one more important concept called as increase of entropy principle. So we have considered a cycle which is made up of two processes. One is an arbitrary process which can be either reversible or irreversible, and the second process is strictly internally reversible. Now, from Clause's inequality we defined that this particular process or difference in entropy is greater than or is equal to entropy transfer, and thus the change in entropy is always greater than or equal to delta Q by T. Now here, before we conclude, let me draw a line that ds is greater than delta Q by T is always for irreversible process, which is called as inequality. This is an inequality, or it can be for an actual process, as no processes are reversible in nature, all are irreversible or actual processes, and this ds is equal to delta Q by T for reversible process. And we know why the difference between reversible and irreversible. It is because of the irreversibilities that are present. So the conclusions here are: the entropy change of a closed system during an irreversible process is always greater than the integral of delta Q by T. That means this expression is always greater, evaluated for that process. Some entropy is generated or created during an irreversible process. The meaning of delta S or change in entropy, okay, the change in entropy is greater than entropy transfer delta Q by T implies that some entropy is generated or created, okay, during an irreversible process. The entropy generated during a process is called entropy generation. So since it is greater, this is called as entropy generation and given the symbol Sgen. This also we have covered. Now the difference between entropy change of a closed system and the entropy transfer is equal to entropy generation and is given by the equation delta S of the system. Now system will define that how we are going to consider this change in entropy and how we are going to write this. The other point, an important point here is the Sgen is always a positive quantity or 0. So this Sgen what you are going to write is always a positive quantity, is greater than 0. Okay. So again for irreversible process. In a limiting case is equal to 0 for a reversible process. Okay. Now since it is a positive quantity, this line is important. It slowly depends on the process, okay, whether it is a reversible process or irreversible process. Now remember here, I want to bring it one point clear, that entropy is a property of a system under consideration which doesn't depend on the path followed. It depends on the states, initial and final states, and hence entropy is a property of the system, whereas the set parameter, that is entropy generation, it depends on the process. It depends on what part that is selected. Hence, it is not a property of the system. Okay, so this is one of the important conclusions that we are going to draw here. So, in the absence of any entropy transfer, the entropy change of a system is equal to entropy generation. If that above equation is considered here, which is called the delta S of the system, which is equal to S2 minus S1, okay. So this expression is equal to what? Integration of delta Q plus Sgen, okay. Integration of delta Q, say from process 1, delta Q upon T plus it is Sgen. So in absence of this entropy transfer, the generation is equal to, entropy generation is equal to change in entropy. So that is the meaning of this line. Next, let us understand what exactly you mean by increase of entropy principle. So with the help of previous concept, that entropy generation, how it is led to the entropy or increase of entropy principle. See that. Now if you consider an isolated system or simply an adiabatic closed system, the heat transfer for that is 0 and the entropy change is 2. Delta S of an isolated system is greater than or is equal to 0. This particular equation is obtained from this. We already written that delta S of the system is greater than or is equal to 0. Okay, or if at all I have to write it for delta Q by T. Now since for an adiabatic system, closed system, heat transfer is 0. Okay, so this becomes 0. So I have delta S. Now the system is what? Is an isolated system. Hence this expression is written. Delta S of an isolated system is greater than or is equal to 0. Again, the equality and inequalities are fixed. Equality for a reversible process and inequality is always for irreversible or an actual process. Now this equation can be expressed as the entropy of an isolated system during a process always increases. So this says that though we consider it an isolated system, the entropy always increases greater than 0. That means it is going to be positive and hence always it increases or in the limiting case of a reversible process, okay, then this equality is valid for a reversible process, but it will never decrease. That is the important thing. Okay, it will remain constant, that is 0, or in other words, it never decreases. This is known as increase of entropy principle. So if any process that occurs in nature, if it is not a reversible one, then it always leads to generation of entropy. So that principle is called as increase of entropy principle. Okay, for example, if I take this, let's take an example of this, where I have shown that the system is isolated. That means there is no interaction of energy to or from the system, whereas there are subsystems inside this isolated system. Hence, the total entropy of all the system leads to the entropy of an isolated system and is always greater than 0. That is the meaning of increase of entropy principle. So there is some subsystem 1, subsystem 2, subsystem 3, so and so forth. There are n subsystems. Okay. Therefore, total entropy, which is called as delta S total, is equal to, if I elaborate that, delta S total is equal to, it is entropy of system 1, entropy of system 2, entropy of system 3, so and so forth, entropy of system n, which is written in the summation form as the summation of I stands from 1 to n, okay, where the number of subsystems are from 1 to n, and the change in entropy delta S I is always greater than 0. Okay, this is always greater than 0. So this is the increase of entropy principle. Or in other words, another example if we take, which consists of an isolated boundary, system boundary, in which I have a system and surroundings together. So here this is a piston cylinder arrangement where the mass enters in or comes out. Obviously it is going to be an open system, and heat transfer from system to surroundings, but there is no mass transfer, heat transfer or work transfer from the isolated outside boundary into the isolated inside boundary. Hence it is called as an isolated system. Universe, for example, is an isolated system in which there is no mass, heat or work transfer possible. Whatever is there, that is within. So if I consider that as an isolated system boundary, the system is interacting via mass, via heat, or maybe via work. So under such conditions, what I can write is delta S generated, okay, or S generation is equal to delta S total, okay, delta S total. So this is delta S total, which is equal to the sum of delta S of the system plus delta S of the surroundings. So this is as per the summation, okay, delta S of the system under consideration plus it is delta S of the surroundings. And if you look into this, the sign value is always greater than or is equal to 0. So this value is always greater than or is equal to 0. So if the processes that are taking place between system and surroundings within the isolated system boundary are reversible, then Sgen value is equal to 0. So I'll be writing here again clearly, okay, if Sgen is equal to 0, again this is for reversible processes between system and surroundings of an isolated system. If this Sgen is greater than 0, then it is for irreversible process. Okay. However, to conclude here, the summary is that some entropy is always generated during a process. Since no actual process is truly or strictly reversible, all processes that are happening in this world are irreversible, and hence we can claim that some entropy is always generated during a process, and therefore entropy of the universe, if I write, is continuously increasing. Okay, entropy of the universe is continuously increasing. Second, the more irreversible a process is, the larger the entropy generated. The larger the entropy generated. Okay, so it depends on the amount of entropy generation, which internally depends on how many irreversibilities that are present. If irreversibility amounts to less, then entropy generation is less, but it never be equal to 0 except if it is a reversible case. But in actual case, all the processes are irreversible. So that we can say the increase of entropy principle does not imply that entropy of a system, okay, entropy of a system cannot decrease. This is very, very important. Entropy principle doesn't say that the entropy of a system cannot decrease. It can decrease. It can be less than 1. Okay. For example, the entropy change of a system, in the previous numerical we have seen that the entropy change in few cases it was negative. Okay. So this entropy change can be negative. Entropy of system can be negative during a process, but entropy generation cannot be, because entropy generation doesn't depend on the end states, it depends on the process. If the process is irreversible, it is always greater, it is a positive quantity. In a limiting case, if a process is reversible, then it is equal to 0, but it cannot be negative. Whereas the entropy of a system or entropy change of a system can be negative. For example, okay, now here I have shown one example where the system and surroundings are considered. So I'll be drawing that here once again. Let me draw the arrangement. So there is a random isolated system boundary, okay, which consists of a system under consideration, a piston cylinder arrangement. Okay, a piston cylinder arrangement. So this particular system, delta S of the system, is having -2 kilojoule per kg Kelvin as the entropy of the system, because heat is being transferred, let's say, from system to, so this is what is the surroundings. So this delta S of the surroundings is equal to, has some value. Okay, so that value is already given there. Delta S of the system is, let's say, 3 kilojoule per kg. Or if it is total, then it is only kilojoule per Kelvin. Okay, so in such condition, if I calculate what is delta S gen, S gen is equal to delta S total. So you have to add the two components of an isolated system to evaluate at generation of entropy. So here it is delta S of the system under consideration plus delta S of the surroundings. So delta S of the system is how much? -2, whereas delta S of the surroundings is +3. So it is going to be +1, which is greater than 0. So this is how the generation, entropy generation can be understood. Okay, so this is equal to 1. Okay. So here we can say that the increase of entropy principle can be summarized as follows. This is important. Okay, S gen if it is greater than 0, then irreversible process. If it is equal to 0, then it is reversible process. If it is less than 0, is impossible process. Okay, it cannot be. So the same conditions you have already seen in second law as far as the efficiencies are concerned. So here we can summarize that Sgen is given by these conditions. Okay. So let's take up few numericals on entropy generation, and let's see that how we can calculate the entropy generation. Now the statement, I'll read it once again. A heat source at 800 Kelvin loses 2000 kilojoule of heat to a sink at the two cases given there. Case A 500 Kelvin and case B 750 Kelvin. Determine which heat transfer process is more irreversible. So this is the question asked. So these are the diagrams. Let's proceed to understanding the numerical. Understanding this entropy is a bit abstract, but it is simple. So the two cases are, in case A we have a source and then we have a sink. So you can just replace this and there is a direct loss to say A, which is maintained at 800 Kelvin. So this is the source and this is the sink. So this is maintained at 800 Kelvin in case A, and heat is rejected how much? 2000 kilojoule. To a sink which is maintained at 500 Kelvin. And in case B, source which is again at 800 Kelvin is connected to sink which is maintained at, say in the second case, 750 Kelvin, case B 750 Kelvin, but again rejects the same amount of heat, which is 2000 kilojoule, which is more irreversible. So as I already mentioned, which is more irreversible means in which case entropy is more generated. So obviously where irreversibilities are more, entropy generation is more. So based on that understanding, we have to solve this problem. So let's take up case A. For heat transfer process to a sink at 500 Kelvin, what are the equations? So I'll be writing here that for case A, delta S of the source, okay, entropy for 800 Kelvin is Q divided by T, Q of source divided by T of source, Q of source divided by T of source. So entropy S is Q by T. Always we have to remember the same thing and then calculate. So heat from the source is 2000 kilojoule. Obviously since heat is lost from the source, so by sign convention it is minus, divided by T source to which it is rejected. It is rejected to 500 Kelvin. Okay, so therefore the entropy generation in this case is minus 2.5. Is minus 2.5 kilojoule per Kelvin. Okay. Similarly, if this is the amount of entropy that is present at source, what is the entropy that is present at the sink? So on the same basis you have to calculate. So delta S of the sink is equal to Q of the sink divided by T of the sink. Now since 2000 kilojoule of heat is absorbed from the source but is rejected to sink, so by sign convention now here we have positive 2000 kilojoule. Okay, the source is 800 Kelvin, not 500. So at the sink, what is the temperature? Temperature is 500 Kelvin. So if you take the ratio, it's going to be plus with sign, it is 4 kilojoule per Kelvin. Now to evaluate delta S gen, okay, or S gen for that matter, generation of entropy, is equal to sum of these two, delta S of the source plus delta S of the sink, as we have only these two as subsystems of the system under consideration. So this is the system under consideration. Okay, so this we have to calculate. So obviously, if I substitute, it is minus 2.5 plus 4. Okay, so the final answer is plus 1.5. So here I'll be writing which sign as plus 1.5 kilojoule per kg. So this is the amount of entropy generation if we consider case A. Similarly, you have to calculate for case B, which I'll be doing here. Okay, let's change the values. For case B, the equations are again the same, but only the source, and of course source also will remain same. Sink temperature is 750 Kelvin. Okay, so the value of delta for the source is, this is same, minus 2800. So this will remain as minus 2.5 is as it is. Okay, whereas delta S of the sink, this will remain as it is. Here instead of 500, it is 750 Kelvin, and hence the value of 4 changes to 2.7. After calculation, it is 2.7, and hence the entropy generation is equal to delta S source plus sink. So here it is 2.7. So it comes to finally 0.2 kilojoule. Okay, 0.2 kilojoule per kg. So now we can compare that the entropy generation was higher here, 1.5 kilojoule per kg, and here it is less. So which is more irreversible? Obviously one is having less, or rather one is having higher entropy generation is more irreversible. So in this case, to conclude, okay, case A is more irreversible as we have larger temperature difference. More is the temperature difference, larger is the irreversibility due to infinite temperature heat difference. So entropy generation is more in case of A, whereas it is less in case of B. Okay, so let's take another example. Here I'll read the statement again. Suppose 1 kg of saturated water vapor at 100 degrees Celsius is condensed to a saturated liquid at same 100 degree Celsius in a constant pressure process by heat transfer to the surrounding air, which is at 25 degrees Celsius. What is the net increase of entropy of the water plus surroundings? So what he has asked is net entropy generation. So here you have 1 kg of water vapor and is condensed to saturated liquid. That means heat is lost from system to surroundings. So in this case, you are supposed to find out what is the entropy generation. The solution is that now water is the system under consideration, or for which we can call it as control mass. From steam table we can calculate. Okay, so let's find out what is the, this is the diagram under consideration. So here we have the saturated water vapor at 100 degrees Celsius is condensed, means heat is lost from 1 to 2, so from outside heat is lost. So what is the entropy generation for this particular arrangement? Saturated liquid, after condensation it gets back to saturated liquid. So what are the initial conditions? Initial condition is that we have T1 equal to 100 degrees Celsius and T2 equal to same 100 degrees Celsius, okay, to the surrounding air. So surrounding is nothing but air. So this consists of an isolated system. So when heat is transferred from here to here, for what is total net in entropy generation? So let us first consider what is about the system. So this is the system under consideration. what is delta S for the system. The delta S of the system is nothing but water vapor at 100 degrees Celsius. So to find the amount of entropy change, we have already used this equation to evaluate, which is nothing but SFG. Okay, it is nothing but SFG. Since I am calculating total entropy, so with mass we have to calculate. Now since amount of heat is transferred, because it is getting condensed, the sign is negative. So here it becomes delta S of the system is equal to minus m SFG. So here the value of SFG is to be calculated at a temperature of 100 degrees Celsius from property tables. So since it is given as 1 kg, the mass is 1 kg. Let's find out the value of SFG from property tables. So go to temperature table, simple. So for temperature table, go to 100 degrees Celsius and the value of SFG, that is column number 12. So for 100, column number 12, it is 6.0480, 6.0480 kilojoule per kg Kelvin multiplied by 1 kg. So that will give the total value as minus the same equation, minus 6048 kilojoule per Kelvin. Kilojoule per Kelvin. Now this is the amount of entropy that is lost. How much is gained then? Concerning the surroundings, that is surrounding air is at a temperature of how much? The T air is at 25 degrees Celsius. So once heat is lost from system to surroundings, its temperature is going to be, okay, let's find out. So heat to the surroundings. So if I calculate the amount of heat to the surroundings, it is given by the equation m HFG. So in the previous classes we have seen how heat leads to the equation of HFG. Now since here I am calculating the total heat, not specific heat, so I need to multiply it by m HFG. Okay, so here the value of m is 1, HFG is again to be calculated for 100 degree Celsius. So let's find out the value of HFG for 100 degree Celsius by going to the same temperature table. The value of HFG is column number 9 for 100 degrees Celsius. It is 2257. It is 2257 kilojoule per kg Kelvin. So the final answer here is 2257 kilojoules. 2257 kilojoules. Now we need to calculate what is the value of delta S for the surroundings, which is nothing but Q of the surroundings divided by T of the surroundings as per the just previous numerical. So here we have already calculated Q of the surroundings to be 2257 kilojoule, and temperature of air, which is 25 degrees Celsius, we need to convert this into Kelvin. So it is 273 Kelvin, which is nothing but 298 Kelvin. So the final answer here is 7.57 kilojoule per Kelvin is the amount of delta S of the surroundings. So one we have already calculated for the system, this is this, and second one we have calculated for surrounding. There are only two subsystems here. One is the system under consideration, that is vapor, water vapor at 100 degrees Celsius, which is then condensed to saturated liquid. The another is air, surrounding air. These two form an isolated system boundary. So for this we need to calculate what is the value of S gen. So this S gen is equal to sum of these two, delta S of the system plus delta S of the surrounding. So delta S of the system is minus 6.048 plus delta S of the surroundings is plus 7.57. Okay, The unit is kilojoule per Kelvin. Hence, the final answer is plus 1.522 plus 1.522 kilojoule per Kelvin. This much amount of entropy is generated per Kelvin. That is the meaning of that. And since it is a positive value, you can say that this is a reversible or irreversible process. So this increase in entropy is in accordance with the principle of increase of entropy. Okay, and this process can take place. So this is the final call. Okay. The last component is what are the takeaways from this entropy. Okay, so you are supposed to make a note of this by studying what you have understood from these classes, how to define entropy or what are the characteristics of this entropy. That is the answer for this, the takeaway from entropy. So let me collectively write it so that we can go through this. The first point is, it is clear from the previous discussion that entropy is a useful property, okay, and serves as a valuable tool in the second law analysis of engineering devices. So far we have seen that in the previous classes you have applied a second law to cycles, be it a heat engine working in a cycle or a refrigerator or heat pump. But in entropy we have applied the same to different processes. So hence it is a useful property. Entropy can be viewed as a measure of molecular disorder. So what we can conclude from our studies, right, previous classes, is that it is a measure of molecular disorder or molecular randomness, mixed upness, which we already defined generally in the beginning of this class. For example, if you see this, the entropy exists in various phases of substance. If it is solid, then the entropy is least. If it is liquid, it is higher because molecular disorderness is greater in liquid as compared to solids, and it is highest in gas. So the randomness, the movement of gases is faster in case of gases as compared to liquid and as compared to solid. Now the reason for all this is irreversibilities, which are already discussed. Now what are those irreversibilities? To just list a few: friction, for example. So wherever there is a friction, there is a irreversibility, there is a generation of entropy. Okay. Similarly, mixing, when two fluids mix each other, okay, mixed in each, so that leads to generation of entropy. Chemical reactions, heat transfer through finite temperature difference. One example we have seen, source and sink, maintaining at different sink temperatures, how the entropy can be different. So that is heat transfer through finite temperature difference. Unrestrained expansion, non-quasi equilibrium, compression or expansion always cause entropy of a system to increase. So an entropy generation is a measure of the entropy created by such effects during a process. So this is another outcome. Now the inequality of Clausius and property entropy are modern statements of second law. Okay, so these are the outcomes of defining second law. Okay, the side effects, the byproducts you can say. Okay, the inequality of Clausius as well as entropy are modern statements of second law. Finally, the final statement of second law is the entropy balance equation that includes generation of entropy. So these are the takeaway from entropy. Thus we conclude this class on the final unit of entropy. Go through the videos again, make a detailed notes on entropy, follow the numericals, go through the property diagrams, property tables which I have mentioned. Throughout this unit I will be using these two books. One is Sontag Van Valen, another is Eunice Sanjil. Still if you find any difficulty, you can always WhatsApp me or can call me and ask for the queries. Okay? Thank you.